In Section 5 of Chapter 15, we will be discussing acid-base indicators. When performing a titration, there are two methods for determining the equivalence point. You can measure the pH during the titration with the pH meter and then plot pH versus the volume of your titrant added, like we see here with this pH curve. Then we look for the vertical region right here to determine the equivalence point. We can also use an acid-base indicator. This marks the end point of the titration when it changes color, but if you plan out your titration well enough, your equivalence point and your end point, although not the same, can be very close. Most acid-base indicators are large molecules and are weak acids, and we will use HIN to represent them in the generic equation. Acid-base indicators will exhibit one color when the proton or hydrogen ion is attached and another color once it is donated. Phenolphthalein is a commonly used acid-base indicator. It is colorless as the acid, and then once it donates the proton and becomes the conjugate base, it is pink. You can see that this hydrogen in the acid is now missing in the conjugate base. Here is the generic equation that we can use to represent acid-base indicators. In the phenolphthalein that we just looked at, the acid form HIN, that was the colorless one, and the conjugate base IN minus was the pink. You might be asking how much of the conjugate base, IN minus, must be present for the human eye to detect that the color is different from the original one. For most indicators, about 1/10 of the initial form must be converted to the other form before a new color is apparent, as seen here in this equation. We will assume that in a titration of an acid with a base, the color change will occur at a pH where this equation is true. So bromothymol blue is a commonly used indicator. It has a Ka value of 1 × 10 to the negative 7th. It is yellow as the acid, and it is blue in its conjugate base form. So if we add this to a strongly acidic solution and then we titrate it with sodium hydroxide, we would like to know what pH will the indicator change color. We said we would see a color change when 1/10 of the original form had been converted to the new form. So we will have a concentration of both the conjugate base and the acid, and we can use the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation will allow us to solve for the pH using the pKa and a ratio of 1 to 10 for the conjugate base to acid concentration. pH equals the negative log of 1 × 10 to the negative 7th, the Ka for the bromothymol blue, plus log of 1/10. When I solve, I get 7 minus 1, or a pH of 6. So in this situation, we looked at an acidic solution where we added the indicator and went from yellow to blue. But if we were talking about adding the indicator to a basic solution, we would be going from blue to yellow. The acid form is yellow and the conjugate base version is blue. So for this ratio, where we want 1/10 of the initial form converted to the other form, we get this equation. If we use the Henderson-Hasselbalch equation here, we get pH equals the pKa plus 1. So in this case, pH would be 8. Therefore, the useful pH range for bromthiamyl blue is from 6 to 8. So generally, for a given indicator, the useful pH range is the pKa plus or minus 1. The useful pH ranges for several indicators are shown in this table. Here is the bromthiamyl blue. Notice the pH range is from 6 to 8. It is really important to be able to choose an indicator for your titration based on its useful pH range. For a titration with a strong acid and a strong base, like hydrochloric acid and sodium hydroxide, you can see that the pH changes very quickly with just a small volume added. So there is a wide choice of suitable indicators. The results will agree within 1 drop of the titrant. So you can use an indicator anywhere between a pH of 5 and 9. This vertical region right here. The previous graph showed a strong acid that was titrated with a strong base, and there was a very long vertical region around the equivalence point. But when we start looking at weak acids, there is a much smaller vertical region around the equivalence point. You don't have as much flexibility in choosing an indicator. We have to choose an indicator where the useful pH range has a midpoint as close as possible to the pH of the equivalence point. This equivalence point appears to be around a pH of 8.7. So a good indicator choice would maybe be something like phenolphthalein that has a useful pH range between 8 and 10. Methyl red would not be a good choice. It would change color between a pH range of 4 and 6, and it would change color well before the equivalence point. So the end point and the equivalence point would be very different. Remember, we'd like to assume that the end point and the equivalence point are the same.